Good morning to all of you.
Morning, sir. Good
Good
morning, sir.
morning, sir.
Yeah,
Good morning, sir.
yeah, good morning, good morning. So, is my screen visible?
Yes, sir.
Okay. So, yeah, I welcome you all to this course. So, first, I will just discuss what is going to be taught in this course, and then we will start the lecture. So, as you know, the course name is Finite Element Methods and its Application to Marine Structures, and the course code is AML 706. And I am going to teach this. I am B.P. Patel from the Department of Applied Mechanics. And so, if you see here, the course content, it says, no, the course content is having first starting with variational approaches for solving differential equations. So we are going to discuss the approximate analytical solution of differential equations as a precursor to finite element method. And in this particularly, we will discuss two approaches. One is better residual and methods, and second is Rayleigh-Ridge method. So that is what we will discuss under this approximate analytical solution of differential equations. And then we will move on to finite element. So basic steps of finite element method, that is what are the steps involved in the overall finite element procedure. And mainly we will be discussing the displacement based formulation. So in the displacement based formulation we will discuss one dimensional elements. So in one dimensional elements we will discuss truss element, beam element, frame element. So those are the one dimensional elements I will be discussing. And then we will move on to two dimensional elements, and in two dimensional more focus would be on isoparametric formulation as you see here. And in isoparametric formulation then we will discuss plane stress elements, plane strain elements, and axisymmetric elements, solid elements. So these are the way different types of elements. So like no, yeah, any engineering structural mechanics problem you have to solve. So if you want to analyze, let's say, ship or a submarine, so you will have various structural elements. So those structural elements can be modeled either as truss beam or plane stress, plane strain elements, or plate bending elements, or solid elements. So of course the choice is depends upon the geometry and boundary condition and supports and interconnections. But no, once you understand what are the different types of elements and what are the assumptions made in those and how they are formulated, so you should be able to choose appropriate element for the structural system you want to model. We will also discuss what are the convergence criteria, and in particularly the the CRD formable beam elements and plate elements. There is a phenomena called shear locking. So we will discuss that shear locking and how to eliminate that, and what are the uh, different concepts like reduced integration, modified shape functions, and so on. So we will discuss on that, and then the last topic will be dynamics problems. So quite often, no, you have to include the inertia forces in the analysis. Most of the time, of course, you end up doing static analysis where you neglect the dynamic effects. But many a times you have to consider the dynamic effects, so inertia forces. And for in that we will discuss dynamics problems, and then we will discuss how to formulate a dynamics problem, how to get the additional mass matrix which is involved in these problems, then how to solve an eigenvalue problem, and how to do the transient response analysis. So those are the things we will discuss in the dynamics problems. So yeah, so these are the topics which we are going to discuss, and if you see the books are which you can refer, and some part of whatever I will discuss will take from J.N. Reddy. So first book is Finite Element Method by J.N. Reddy. Second is Finite Element Analysis by P. Sesu. So you can find many other things I will be discussing in these two books. And then there are also books like Introduction to Finite Elements Engineering by Chandru Patla and Belungundu. So this is also a useful book. So first three books you will find actually more useful. And of course there are other books, Finite Element Method by Jimkis and Taylor, then concept and application of finite element analysis by Cook, Malkus, Plesa and Witt, and finite element method in engineering by S.S. Rao. So these are the books, mostly you can find the material which I am going to discuss in Jain Reddy, Sesu and Belungundu and Chandru Patla. So first three books. So you can just look at these books. And then basically, as far as the course evaluation is concerned, so you will have one minor, so the weightage of that is going to be 30%, and there would be one major at the towards the end of the semester, and the weightage of that is going to be 50%. And you will also have to some, I will be giving you some assignments and conducting quizzes, so all that will have a weightage of 20%. So this is how the final grade is going to be based on this: 30% minor, 50% major, and quizzes and assignments are at 20%. And as I already said, I'm B.P. Patel, Applied Mechanics Department. My room is block 4 to 46. So of course, so this is what about the course content, evaluation policy. So now the yeah if you have, of course, when I'm teaching, if you have any doubt and any question you want to ask in between, you can unmute yourself and ask that doubt and question. You can also ask at the beginning of the class. You can also ask doubts and questions at the end of the class. That is how now you can ask your doubts, and of course you can visit to my office anytime, if you want to ask any doubts and questions. So this is how the class will be. So yeah, I think so this is what I wanted to discuss in this course content. So yeah, now let me, yeah, so now is my screen for Windows journal is visible? Hello, is my screen a
Yes,
Windows
sir.
journal screen is visible?
Yes,
Okay,
sir. It is
so
visible, sir.
okay, yeah. So yeah, let me start. So as I already said, the course name and everything. So now let me start. So this is oh, it is not writing. So let me close the file and open it again. Yeah. So this is the course, as I already said, AML 706. And see, as I know, you already know the class is in Impartus. The videos would be automatically recorded, so I would be uploading them maybe in the evening of every lecture day. So you can go through. I will also be PDF of whatever I write in this Windows journal. The PDF of that also will be uploaded under backpack in the Impartus. So you can also see that. So when you are you want to study, so this is course is AML 706, finite element method, and its application to marine structures. So now what now if you look at the general approach to any engineering problem solving, so what we do is now you have a, let's say, a physical system, and that physical system we want to study. So sometimes we want to study the relationship between input and output for different, either for a particular set of system properties or maybe wiring system properties. So that most of the time our interest is to study the relationship between input output for different system properties. System properties may meaning the dimensions, material properties. So that is what most of the time we are worried about, the system properties. So now what you can do is, when you want to study this any physical system, so this input output relationship, so what you can actually do is, one is that if the system is already existing, you can conduct experiments, or if it is a new system you are actually designing, so then you have to build the system, you'll have to make the prototype and then do the testing. So that is one route, and that I'm putting here as experimental techniques. So when you want to study the relationship between input and output for different system properties, one is that you conduct the experiments. So you know through the experimental techniques route. The other is no, but of course you know that this is costly and time consuming, and particularly if it's a new system you want to do the optimization, so it will not be possible actually to make a different physical system with different system properties and study the input output relationship. So the other easier approach, and which can be used for the optimization of the system, design and optimization of the system, is through mathematical modeling. So the other is mathematical model. And what we mean by mathematical model is usually we deal with what are known as either ordinary or partial differential equations, and sometimes maybe combinations or a combination of algebraic equations also, together with boundary and initial conditions. So you have set of ordinary. So I am presuming that you would have done some courses on this, mathematics courses on ordinary and partial differential equations. So these are set of either ordinary or partial differential equations. And in addition, no, these may be appended with and or sometimes only algebraic equations may be there, or sometimes only differential equations may be there, either ordinary or partial, or sometimes only algebraic equations. So that is algebraic relationship between the input and output. So and our algebraic equations. And together with boundary and initial conditions depending on the problem. So sometimes only boundary conditions may be there, sometimes both boundary and initial conditions may be there. So boundary and initial conditions. So this is what we mean no, what we are going to do in the course is the this mathematical model, which is a set of ordinary partial differential equations, algebraic equations, plus boundary and initial conditions. So now once we have this mathematical model, and of course this we derive from the physical laws governing the physical system. So this mathematical model itself is derived based on the physical laws governing the system. So for example, mechanical systems, we use equilibrium equations essentially to arrive at the mathematical model. So equilibrium equations, equilibrium of forces and moments. So now once we have this mathematical model for any given physical system, either it is an existing system or a new system which we want to design, so we will have to solve this mathematical model. So because this is a set of algebra, most of the time differential equations, so we will have to solve these. So the solution of these differential equations is could be sometimes it is possible to get the exact analytical solution. So that is one is exact analytical solution. So that is one. possibility, but you will find that many a times for real life systems it is difficult to obtain, or it is sometimes even impossible to obtain the exact analytical solution. So what do we mean by exact analytical solution is that it satisfies, when you say exact analytical solution, so it satisfies differential equations, boundary and initial conditions exactly. Satisfies differential equations, boundary and initial conditions exactly. So that is one, but as I said, most of the time it is not possible to obtain the exact analytical solution, particularly for the complex systems. So, for example, if you look at the structural system of a ship or a submarine, so it's quite complex. Know you the kind of interconnections it has, the varying properties, it has a geometry, it no kind of geometry it has. It will not be possible to obtain exact analytical solutions. So then we look for, of course, sometimes we do take components, and for that component we idealize its boundary condition and geometry, and then whatever possible exact analytical solution for that we use sometimes those in the initial design phases. So we do that, of course, but then that is based on some approximations. So then another approach is to get the approximate analytical solutions. So exact means it exactly satisfies the differential equations and boundary plus initial conditions, and approximate analytical solution means it approximately satisfies, so it will not exactly satisfy. That is, in all differential equations, boundary conditions, left hand side will not be exactly equal to right hand side, but it would be a minimum in some sense. The difference would be minimum right hand and left hand side. So we call that as approximate analytical solution. Approximate analytical solution. And this is also when we say approximate analytical solution. So we kind of looking for a solution which is no valid for the domain, but no, the differential equations and boundary conditions are not exactly satisfied. They are satisfied no, in an approximate sense, but we are still looking for a solution which is valid over the entire domain. So this is also sometimes quite restrictive. Although compared to exact analytical solution, we can obtain the approximate analytical solution for a wide range of problems, but that is also restrictive in terms of its accuracy, and also obtaining the solution for the entire system if the system is quite complex. So then the most commonly used tools we use is what is known as the numerical solution. So these are also approximate solutions. So numerical solutions. And in the numerical solutions of mathematical model, which is differential equations, or the partial differential equations, or algebraic equations, and whatever we have, so there are different methods. So the earlier most common method was finite difference method. Of course, now most commonly used methods are finite difference and finite element and finite volume method. But earlier it was FDM. FDM means finite difference method. So what is done is that you have differential equations, so convert them using the finite difference definitions. You convert the differential equation into difference equations, and then no the difference equation means algebraic equation, and then you solve that algebraic equation subject to, of course, the appropriate boundary condition. So that is finite difference method. We are not going to discuss, of course, finite difference method, and then the finite element method, and that is what we are going to discuss. So in finite element method, what we do is we discretize the entire domain into smaller subdomains. We call them as finite limits, those subdomains, and assume an approximate solution within each domain, and determine the unknown constants in that by satisfying the differential equation in approximate sense, and or minimize the total potential energy functional or Hamiltonian, and develop the element level governing equations, assemble them, impose boundary conditions, and then solve the problem. So of course we have the as the course itself is on finite element, so we are going to discuss this throughout the course. So we will now develop understanding about what are the various concepts in finite element. Then the third is finite volume method. Finite volume method is basically it considers the basically the balance of the various fluxes or the quantities over a volume, and then the the differential equation algebra converted into algebraic equations, and they are solved. So that is finite volume. You will find that finite element method is more popular in solid mechanics problems, structural mechanics problems, whereas finite volume method is more popular in fluid mechanics problems. So of course I will not be discussing that. So as I said already, I'm going to discuss only finite element method, but I just wanted to give you an idea that what are the different methods available, and I can be used. So the finite volume is, as I already said, most of the CFD softwares are based on finite volume method. Of course, sometimes it is not that finite element cannot be used for fluid dynamics problems. It can be used, and there are some packages which are based on finite element for fluid mechanics problems. But most of the time, you will see that solid mechanics problems are solved using finite element method, and fluid mechanics problems are solved using finite volume method. So there are other methods like BEM, boundary element method, or sometimes it is also referred to as BIM, boundary integral method. So boundary element method or boundary integral method. So in this, most of the time in finite element, finite volume, actually the domain is discretized, and then the solution of the that means when the differential equation governing the problem, they are basically defined over the domain of the problem. So we are kind of looking for the approximate solution or differential equation over the entire domain in these two approaches, whereas in boundary element method only the boundary is discretized, and the boundary problem the boundary equations the boundary conditions, they are solved in an approximate sense. So that is known as boundary element method, where only boundary is discretized. So for example, if you have 1D problem, in boundary element method you will only concentrate on two boundary points. If it is a two-dimensional problem, so the boundary would be only curves or lines. So it would reduce to 1D problem because the boundary is only one-dimensional line or curve. And if it is a 3D problem, the boundary would be bounding surfaces would be there. So boundary would be two-dimensional. So a three-dimensional problem in boundary element, a boundary integral method would be reduced to a basically two-dimensional problem. So dimensionality reduction is also there, but usually this is more complex because within the domain the differential equation has to be satisfied exactly. So those are known as Green's function. So obtaining the Green's function itself is becomes sometimes a difficult task. So this is not very popular, although people do use it, particularly for fracture mechanics problems. This is quite useful for there is a singularity in the stress and strain field near the crack tip. So you use this boundary integral method or boundary element method there. Then because in the finite element finite volume you are discretizing the entire domain, and if there are large particularly for structural mechanics problems using FEM, so if there are large deformations, so the elements get distorted, and once the elements the assembly of those subdomains, smaller domains, gets distorted, the accuracy is lost. So to overcome this problem, there is another class of methods which are becoming popular now, are known as meshless methods. So meshless method means the domain is actually not discretized. Only discretization is done in the sense that over the entire domain there are points created, arbitrary distribution of points, and you select a certain set of points around a one particular point and assume an approximate solution. Of course, still you have to satisfy the differential equation in approximate sense and all of the governing equations and solve the problem. So since the domain is not discretized into smaller subdomains or finite elements, so the problem of distortion is not there, distortion of those elements. So no, sometimes in finite element involving finite deformation, large deformation, you might have to do remeshing. So that kind of issues are not there in meshless methods. Then in the literature, if you see also, for solving the differential equation, there is also a method called differential quadrature method. So again, no, the you consider the differential equation, and using the quadrature formula, the different derivatives are expressed in terms of a difference of the values at the different points over the entire domain, and then you solve the problem. But those the derivatives are expressed what is known as the differential quadrature approach, and therefore it is known as differential quadrature method. So then there is also XFEM, extended. This is known as extended finite element method. X stands for extended. So XFEM means extended finite element method. So particularly this is used for fracture mechanics problems or problems where there are singularities. That means for a if you have a crack in a body, so at the crack tip, no stresses would be infinite. So that is known as singularity stresses and strains. So you call that as singularity there. And to solve those kind of problems, or even you want to under the given loading, either monotonic or cyclic loading, there might be crack propagation. So these problems can be solved using FEM, but accuracy is less and you require large number of elements. But XFEM, no, you add some extra shape functions near the crack tip, and then solve the problem, so it becomes computationally less involved and gives more accurate solution. And then no, there is also known as SFEM, smoothed finite element method. So, as I was mentioning during the discussion on the course content, that there is a shear locking in shear deformable no beam elements or plate elements. So, there are many approaches. One of them is known as the smoothed finite element method. So, you smooth out, so whatever assumption you make on the approximate solution within the domain, you smooth that out, and so that is known as the smoothed finite element method. So yeah, so these are the various methods which are available no under this solution of basically mathematical models or differential equations. So I am as I said, no, I am going to discuss this only finite no finite element, and that's more be although no, when you learn thoroughly this finite element method, you can also easily learn the other techniques, because many of the things would be actually common. So yeah, so this is where no you can no you can visualize where the FEM stands among so many methods which are available. Of course, FEM is quite common for solving solid mechanics or structural mechanics problems, and there are packages like you have ANSYS, Abacus, NISA, COMSOL, Nastran. So there are many softwares which are available, commercial softwares, and they have no extended no extensive element library. You can solve various kinds of problem using those packages. Of course you need to learn, and of course in this particular course we don't have any lab hours, so the packages are not included in this, so we are going to do more of theory. But then you can on your own initiative you can learn either say ANSYS, Abacus. So those are most commonly used softwares, so you should learn those up definitely. And so that you are able to solve problems. Maybe I will try to arrange a few lectures on demo on this software, so that I will try to do if it is possible. So yeah, with this introduction to the solution of mathematical model, different techniques for the solution of the mathematical model. So let me start with just very simple examples of mathematical models, how we develop them, because we will be using these mathematical models, differential equations subsequently. The either differential equations are energy functionals for developing the element level governing equations. So let me discuss that. So yeah, please ask. If you have any doubt in between, you should stop me and ask. Although I will continue the lecture, but you can stop anytime. Please stop and ask doubts and questions. Hello,
Yes,
are
sir.
you listening? Yes.
Sir.
Yes, sir.
Yes, sir.
Yeah. So please, you stop me whenever you have any doubt or you're not understanding anything or everything. You should stop me and ask. So the next is I'm going to first take some examples on how we, although some of these things you might have done earlier, so maybe kind of repetition. So we are going to take some examples on mathematical model. So first example I'm going to take is example 1 is the example of a rod uh, which is under the axial load. So typically we call that as a truss. No, not the truss structure, but the truss structural element. So some kind of stiffener and all, sometimes although stiffeners may also undergo bending, but sometimes you can idealize that, or maybe let's say a missile is there. Missile is subjected to thrust forces, drag force, and those kind of things. So predominantly the deformation is axial deformation. So that kind of structural element can be modeled using this. So I'm taking an example that this is a rod, and the diameter of the rod compared to length of the rod is much smaller. So this is length of the rod, and diameter are correct typical the cross sectional dimension. So d is much smaller than length, so that's an approximation. This is subjected to distributed force along length. So let us say that this distributed force is q, and this is, let us, made up of a material whose Young's modulus is E and the cross sectional area is A. So we call this as the axial stiffness, which is EA. And so this is the rod we are considering, and this end is fixed. So when I show something like this, that means it is actually fixed. And so now if we want to develop the mathematical model for this, so basically we need to look at what variable we are going to choose. So I'm going to write everything finally in terms of displacement along x direction. So let us say here we have x coordinate, and along the x direction the displacement is u. So I'm going to express everything in terms of that. So for that we look at the equilibrium equation. For developing the equilibrium equation, a differential equation. So we are taking a small part of this. So let us say we take a cut section over here, another cut section over here, and then let us say these two sections are separated by a distance delta x. So now for developing the mathematical model, what we do in this case, this is a solid mechanics problem, so it involves equilibrium, and it is not under motion, of course, so there's no vibrations. So it is subjected to this load q gradually, and then it deforms and it stays in that deformed configuration. So that is why we are calling it as a equilibrium problem. So here we are considering to derive the mathematical model, we are considering equilibrium of a small element, small, let me call it as small part of length delta x. So now the first step in this is to draw the free body diagram. So you should be good at drawing the free body diagram. So we want to first we have to identify for what we are drawing the free body diagram. So in this case we want to draw the free body diagram of this part. So we sketch it separately, that only part, and we show all the forces in this, whatever forces are acting. So one is this distributed load which is there, q is there, its length is delta x, and then because it is only subject to this axial force q is force per unit length, so its unit would be something like newton per meter. So you will have this q, and in addition to this, when you look at, let's say, the left section that is over here, so when you look at this portion, this part which is on the left side will be exerting some force onto this particular part, no, the part which we are calling as of length delta x. So let us say that force is axial force, and it is given by F. And in general, this force F is going to be function of F. So similarly, when you look at this section, this side, so the right part would be exerting some force on that, and that again is going to be an axial force, and that force is going to change from left to right. So let us say that force is F plus delta F. So now these are all the forces which would be acting in this element. So the distributed force q, which is force per unit length, and then force F, which is along the axial direction at left section, and also there is a force F plus delta F along the axial direction on the right section. And now if you look at the equilibrium, so equilibrium means sum of all the forces must be equal to 0. This is an equilibrium problem, so the we take the forces along plus x direction. So what I am saying is sum of all the forces along x direction equal to 0. This implies that F plus delta F, that is along plus x direction, this is along minus f direction, then this is Q is force per unit length, so the total force would be Q into delta x. Q actually could be function of x. So let us say we have the average value of this, and into delta x would be the total force due to Q, and this must be equal to actually 0. So as you see, of course, this F and F gets cancelled, so we get this delta F plus Q average into delta x is equal to 0. And now we want to develop the basically the governing differential equation at a point. So what we are going to say is that we are going to say that this delta x goes to 0, so that we get the equation at a point. But if we do that as it is in this, so if no delta x goes to 0, so then the left section and the right section would be at the same location. So the delta f will go to 0, delta x would be going to 0, so it would be 0 equal to 0. So that would be a trivial equation. So make it non-trivial, what we do is we divide it by delta x and take the limit, then delta x going to 0. So we write this limit delta x going to 0, whole thing divided by delta x. So we get delta f by delta x over here, and the second, because we are dividing it by delta x, so that goes out, and the q average will become the exact value of q at given x. So then we will just get q. I am eliminating average because when delta x goes to 0, q average will become the exact value of q at this point. So this is equal to 0. Now as you know, the limit delta f by delta x is actually df by dx. So df by dx plus q equal to 0. But we want finally know this differential equation in terms of the displacement u. So what do we do? So how do we write this? So we consider the concept of stress. So we write this force F. No, F will be equal to, at any given point at a given x, F would be equal to normal stress along the x direction. So that is sigma xx into A. A is the cross sectional area. So in this, what we are assuming when we are writing F is equal to sigma xx into A, that means sigma xx is constant throughout the cross section at a given location x. So here in this model, when I'm saying f is equal to sigma xx into A, we are assuming that sigma xx is assumed to be constant through the cross section. So that means it can be, it can be function of x, but it is independent of the cross sectional coordinate. So constant through the cross section, and that is why we are able to write it as sigma xx into A. Class chal rahi hai. So now that is one, that we are writing f as sigma xx into A, assuming that sigma xx is uniform, and this would be true if no the cross sectional area is much smaller compared to length, or the cross sectional dimension say d is much smaller compared to length of the element. So you can nearly assume, and the load is only axial load, so then we can fairly accurately say that sigma xx is going to be uniform along the cross section, and sigma xx is I hope you know that sigma xx is normal stress along x direction. So now the because we want to bring in actually displacement, so then we write stress in terms of strain. So then we use what is known as stress strain relation. So in the stress strain relation, what we are going to say here, that only one stress component, that is only sigma xx, is non-zero in this problem, and other components sigma yy, sigma zz, and all the shear stresses are actually zero. So this is a uniaxial problem, and material is, let us say, linear elastic isotropic. So in that case, we can simply use the Hooke's law and say that sigma xx is actually E times epsilon xx. Where E is Young's modulus, as you know, E is Young's modulus, Young's modulus of the material, and we are assuming that this material is linear elastic isotropic. So the assumption made in this, when we should be clear about all the assumptions. So if material is linear elastic, so that means when the loads are removed, it comes back to its original configuration. So it is elastic. Material is also isotropic. The properties are same in all the directions. Although this is not very important, because as long as we know the Young's modulus along the x direction, we can use this. Of course, we still want to say that there is no coupling between the shear and normal stresses. So shear and normal stress and strain components. So material is linear, elastic, isotropic, and the state of stress is uniaxial state of stress. So
Sir,
under these assumptions, you are able to write this. Yeah, yes, please.
sir, in this you have written sigma xx is assumed to be constant throughout the cross section area.
Yeah,
So that means that the sigma xx does not have any component along y and z direction of that area, no sir, that plane, yz
yeah.
plane.
Sigma xx as such is the stress component along x direction. So it doesn't have any component as such.
So
So yeah.
yes, sir, yes, sir. So that's why it is constant in those direction. Is it the reason? Like,
No, not because it doesn't have component along y and z direction. What we are saying is that, let's say if you talk of a beam, so I think you will have idea about beam. So beam,
yes,
in
sir.
case of beam, there are transverse loads and no ultimately bending moment. So in that you get the still the stress component is sigma xx, but that varies through the cross section. So here we are
Okay,
saying loading is along the axial direction, and the
okay,
cross sectional dimension is much smaller compared to length. So when we look at the cross section, any point in the cross section, everywhere we have the same stress sigma xx. So that is the
okay,
assumption we are making. Not that it
okay, sir.
doesn't have component. It doesn't. Although no sigma xx is the stress along x direction, so will not have any component along y and z. So y and z components are zero, but it is not constant. Because of that, we are assuming that it is constant through the cross section. Unlike beam
Okay,
problem, where no the stress sigma xx will still be there in a beam problem, but it would be varying across the cross section. So for there, no,
okay,
you cannot write some relationship like this. Most of
okay,
the
sir.
time, there the axial force is actually F would be zero. The integral of sigma xx over the cross section would be zero in a bending problem in most of the problems. So we
Okay,
are differentiating from there.
okay, okay.
Yeah.
Yes, sir. So the material is linear. That's why the sigma xx is constant in the cross sectional problem.
No, it is not also because material is linear. Sigma,
Okay,
material is linear, linear elastic, and that is why we are able to write sigma xx is equal to E into epsilon xx. So that assumption
okay,
is coming in, no, writing this particular relationship. But when I have written here, no, this relationship, F is equal to sigma xx into A, that is because we are assuming that the sigma xx is constant through the cross section.
okay,
So
okay, sir.
this is actually possible if the cross section is dimension is much smaller compared to length, and the loading is only along the length direction. The externally applied load, in this case, this distributed force Q, is along x direction. So if we take any small area in the cross section and find out the force per unit area in that, that would be equal to, if we take the total area and find the force per unit area, you will find the two would be same, and that is why we are
Okay,
saying that sigma xx is constant through the cross section.
okay, sir. Okay.
Yeah. So what I'm saying
Thank
is
you.
that if you say take this cross section and you take a small area, let us say this area, and to find out the total force acting in this area divided by this area, whatever we get, now we take the total area, this total area and total force, and divide by no the total force by total area, that whatever force point area we get, same we will get if we take this one. So that means everywhere, no, the force per unit area is same everywhere through the cross section. Of course, along the length at different cross sections at different x locations, that sigma xx may change, but at a particular x location, the sigma xx is constant throughout this cross section. That is what
Okay, sir.
that's an assumption, and based on that, we are
Okay,
able to write this. And based on
okay,
linear elastic isotropic material, we are able to write actually this sigma xx is equal to E into epsilon xx. No, the material is linear elastic isotropic, and also the state of stress is uniaxial. That is sigma yy, sigma zz, tau xy, tau yz, tau zx, they are all zero. So sigma yy equal to sigma zz is equal to tau xy is equal to tau yz equal to tau zx. So these are zero when I say uniaxial state of stress. And based on
okay.
that, we are able to write actually this relationship. So then ultimately we want to bring in the no displacement. So we also need to talk of the what is known as strain displacement relation. Strain displacement relation. So this we write it as an epsilon xx, normal strain along x direction epsilon xx is equal to du by dx. And I am assuming that, of course, you have some little bit of background on the concept of stress tensor, strain tensor, and the components. So actually, I am assuming that. So no, if you don't have idea about any idea about these things, so please then let me know. So I am assuming that you have done a solid mechanics course, and so you would have learned these. So strain displacement relation, again, we have only one independent component of strain, that is epsilon xx, and that is written as rate of change of u along x direction, so du by dx. Again, in this, we are not taking any quadratic terms, so no, we are neglecting the nonlinearities in this relationship. So that is an assumption, and we call that assumption here is that is small displacement gradient. So du by dx is small, so its square is negligible compared to du by dx itself. So we call that assumption as small displacement gradient. So now we have this the epsilon xx is equal to du by dx. So you put it here, so you can get sigma xx as E into du by dx. I know in this equation, and then when you put it here, you can say f is equal to E into a into du by dx. So you use these three equations. So let me call this as equation 1, this as equation 2, this as equation 3, this as equation 4. So if you use all these equations, so finally using equations 2, 3, and 4, now we can finally say f is equal to, that is sigma xx into a, sigma xx is basically e into epsilon xx, and epsilon xx is du by dx. So if you straightforward substitution, you would see that ef would be equal to ea into du by dx. So finally from equation 1, you get the final equilibrium equation, which is a differential equation in terms of the unknown variable, basically that is your u. So from equation 1, we will get now, if you look at first term is df by dx over there. So f is ea into du by dx, so we will get d by dx of ea du by dx. So this is your f, and plus q equal to 0. So see, this is finally the differential equation governing this problem. And if EA is constant, although EA in general could be function of x, either the Young's modulus might vary along length, or cross-sectional area might vary, or both might vary. So then this would be function of x. But if the cross-section is uniform and the material is same throughout the length, so then this EA would be constant. So then you can take it outside. Otherwise, no, this differential equation is in this form. And you see the highest derivative of u. Here u is your unknown variable, primary variable u, and this differential equation involves the second derivative, highest derivative of u is second derivative, so it is a second order differential equation. So we call this as governing differential equation. Governing differential equation. So since we have only one variable, that is u, and u is the displacement along x direction, so we require only one differential equation, and that differential equation is actually this. And let me call this equation as equation 5. So now finally, no, you have this as the governing differential equation. Now if you want to look at the boundary condition in this case, this is a static equilibrium problem. So initial conditions do not come into picture when we have dynamics problems, time dependent problems. Then initial conditions also come into picture. The differential equation where time derivatives are also involved, then initial conditions also come into picture. But in this problem, this is a statics problem, there are no time derivatives involved, and so it requires only boundary conditions. So the boundary conditions are: one, now if you look at the problem, so this is the problem we are talking about. So as you see, this in the left side, x equal to 0, that is fixed. Why it is fixed? Because no, this is the support over here, it is not, this is not allowed to move along x direction. So actually u is equal to 0 over here. And now if you look at here, this location, right hand side, so there is no externally applied, this distributed force q is there, which is force per unit length. So there is no externally applied concentrated force over there. And since q is force per unit length, and if we take zero length, so if we just take a section over here, a small section like this, so this side there is no force, and this length, this length we are taking zero. So the force due to q is going to be zero. So the net force on this section, you can say, when this distance is going to zero, is going to be zero. So the force there is F, which is sigma xx into A, and sigma xx is E into epsilon xx. Epsilon xx is du by dx. So ultimately, you can say du by dx is going to be 0 at the right side. So the two boundary conditions are, the boundary condition number 1 is that u equal to 0 at x equal to 0. That is one boundary condition. And the second boundary condition is at the right side, as I said, no force. So no f, and no f means du by dx is 0. So du by dx is equal to 0 at x is equal to L. So these are two boundary conditions. And you will notice that when the differential equation, the governing differential equation is second order, the highest order derivative is 2. So then you require two boundary conditions. So these are two boundary conditions actually. So when we solve this differential equation, we will have two unknown constants, and those unknown constants are determined using these two boundary conditions. So yeah, I think yeah, this is
Excuse
where
me,
I
sir.
want to, yeah, this is where I want to stop. Now, if you want to ask questions and doubts, you can ask. I will continue in the next class remaining things.
Sir, could you explain the second boundary
Oh
conditions?
yeah, okay. So see, what I am saying is that if you right side, if you take this section like this, right hand side, this is free, there is no force. And let us say for the time being, I will say that this length is some epsilon, delta, not epsilon. I want to differentiate it from delta x, which be used for deriving the differential equation. So let us say this is delta, and in this, this q is there, and there would be some f over here. So if you now look at the equilibrium equations, we will have minus f plus this q into this distance delta equal to 0. So now because we want to write this condition right at the right end, so that is at x is equal to L. So when at x is equal to L, delta will be going to 0. Delta would be going to 0. So when delta is going to 0, you will get minus f equal to 0, or you can say f equal to 0. Now if you see, f is equal to a into sigma xx, and sigma xx is e into d epsilon xx, and epsilon xx is du by dx. So we get this as a into e into du by dx. And since f is 0 at x is equal to L, this is at x is equal to L, so a into du by dx is equal to 0. Since a is cross sectional area, that is not 0. E is Young's modulus of the material, that is also not 0. So you finally say that du by dx is equal to 0. So that is how we are saying that the boundary condition at the right end is that is at x is equal to L is du by dx equal to 0. Is that clear?
Yes, sir. Thank you, sir.
Yeah. So are there any other questions and doubts? Anybody? Any other question or doubt? Okay, so if there are no other questions and doubt, no, I am supposed to continue till, I'm sorry. Yeah, I'm supposed to continue till, no, 11. This is a 1.5 hours class. So I will continue. I'm sorry, I will continue. Yeah, I will continue till 11. I'm sorry, I thought the class is only of 1 hour duration. It's 1.5 hours. So we are going to have the classes only on 2 days, Monday and Thursday. So it would be 9:30 to 11. So I'll continue. I'm sorry. So yeah, this is so one problem. So that means finally you have, this is the mathematical model of this problem. That is, no, this is the differential equation and these are the boundary conditions. So this together, equation 5, and if we call this as equation 6, so 5 and 6 together basically constitute the mathematical model of this simple problem. So now let me take another example. So this is second example I am taking, which is let's say heat conduction problem. So heat conduction in a fin. So again, I'm assuming that compared to cross section, the length of the pin is much larger. So temperature gradient will be there only along the x direction, and also the temperature gradient is there, of course, only in x direction. Although the heat flow can be there along x direction and also along cross section because of the convection. So the problem I'm considering is, this is the rod and this is the coordinate x over here. The length of this rod is say L, and the thermal conductivity is, let us say, K, and perimeter, the circumference, it could be any cross section actually. So perimeter is P, cross sectional area is A. So that means, let us say it has some cross section, so the perimeter is, I am calling P, and this cross sectional area I am calling as A, and the perimeter is P. So and yeah, there is a convection between this surface of the rod and the surrounding. So let us say we model that convective heat transfer by convective heat transfer coefficient H, and the outside temperature is, let us say, T infinity. So now again we want to develop the mathematical model of this problem. So again we consider a small differential element. So let us say this element of length delta x, and so we draw now what is the energy input to this and what is the energy output to this. So one is, let us say, no, on the left side, from the left side portion, let us say some heat capital Q is entering into this, and in general this total heat entering into the cross section would vary from one location to another location. So let us say this heat flow is going out at the right cross section, and the amount is Q plus delta Q. So there is a change in that, and of course the length is delta x, and also there is a convection from the surface. So through the convection there is also heat going out of this, and that would be no I presume that you know some basic idea about no the convective heat transfer coefficient. So that can be written as, no, heat per unit surface is going to be h into t minus t infinity. So therefore total heat would be h into surface area, so h into basically T minus T infinity, where T is the temperature at that location and T infinity is the surrounding temperature. So this is heat no going out of this small part through convection per unit area, and the area would be basically perimeter P into delta x. So this is the total heat which is going out. I'm assuming that there is no heat generation inside this, so and it is under steady state. So also there is no accumulation of heat inside this. So under steady state condition, this is the input heat flux, this is outgoing heat flux, and this is the outgoing heat flux due to convection. So these are the
Sir,
only, yeah.
sir, this outgoing heat flux should be Q minus delta Q, isn't it, sir?
Yeah, see, the we are taking Q plus delta Q, and this delta Q could be positive or negative. That would depend on the temperature gradient.
Okay, sir. Okay. Okay.
Yeah, so you are right that physically, because there is a convection, so this delta Q is going to be negative. But we are writing no the delta Q as a positive quantity, and it no as a positive quantity, unknown quantity, we are taking it as delta Q. But this can be negative also. So yeah, you are right that it would be actually negative. But as a quantity we take it as positive when we are because when we go along the cross section, so when we are moving along the increasing x direction, so we take these quantities increasing along x direction as a positive convention, like we did in the previous problem. We took f on the left side and f plus delta f on the right side, so in the same logic. So now we write the basically the energy balance. So for this, if we do the energy balance, so now Q plus delta Q is the outgoing flux, minus Q is the incoming flux, no total heat, and plus I'm taking the outgoing heat basically as positive. So Q plus delta Q I have taken positive, minus Q is incoming, and then this H into T minus T infinity into P into delta X, this is also outgoing. And this is under steady state, no heat accumulation, no heat generation, so this must be equal to 0. And again we want to develop the equation at a particular point. So finally we want to say that no delta x is tending to 0. So as it is, if we do in this equation, so delta q will go to 0, delta x will go to 0, so this would be 0 equal to 0, a trivial equation. So then we divide it by delta x and take the limit delta x going to 0. So the first term will give you limit delta x going to 0, delta q by delta x, and that would become dq by dx, first term. And no, this term will be, because we are dividing it by delta x, so we will have only no h into p into t minus t infinity. This is equal to 0. Now comes the now we finally want to write this differential equation in terms of only one primary unknown, that is temperature as a function of x. So now for that, what we need to do is, let's say we consider the heat flux, that is heat per unit area. So and then we write this capital Q, that is heat flow at any cross section, is equal to Q into small a. So A is the cross sectional area and Q is the heat flux, that is heat flow per unit area. And you would know that no, this heat flux per unit area Q can be written as minus K into dt by dx. So this is known as Fourier law of heat conduction. So Fourier law of heat conduction. So in this also we are assuming that the material is actually isotropic and linear, that is means thermal conductivity is independent of temperature and isotropic, so temperature gradient along x direction gives rise to only heat flux along the x direction. So this small q is the heat flux per unit area, heat flow per unit area along the x direction, so that is minus k times dt by dx. So that is heat would flow along the negative direction of this temperature gradient. So if dt by dx is negative, then q would be positive. Dt by dx is positive, then q is going to be negative. So the heat flow would be in the other direction. So now if you put this, so q is minus k into dt by dx, and capital Q is q into a. So if you put all these values, so the first term you will see, this term, this equation you would be able to write, because this minus sign is there, so we will have a minus sign. Then we have d by dx, and then capital Q, no, this q is small q into a, and small q is minus k into dt by dx. Minus is already written over here, so I will have ka into dt by dx, plus we will have this h into p t minus t infinity equal to 0. So now this is the no governing differential equation. This is again for this problem is the governing differential equation. So again, you would see that no either no this thermal product of thermal conductivity and A may be constant along the length, so then that can be taken outside. Even otherwise, the highest derivative of t is going to be second derivative. So this differential equation is going to be a second order differential equation, and it is a ordinary differential equation. Suppose no, if it was a transient heat conduction problem, then we would also consider the heat is stored in the body, and the uh, time derivative or temperature will also come into picture. Then it will become a partial differential equation involving derivatives of temperature with respect to x as well as time. But as of now, because we are considering steady state heat conduction, so it's an ordinary differential equation. Now if you look at the boundary conditions, so again in this let's say the boundary condition one is that at the left end, this end, let us say it is attached to some other surface from which we want to transfer the heat. So this surface is, let us say, at some temperature, let me call it as say T naught. So then at the left end, the boundary condition is that T is equal to T naught. So T equal to T naught. T naught would be a known quantity. So T equal to T naught at x equal to 0. That's one boundary condition. There can be other types of boundary condition. I'm writing just typical boundary conditions to show that what we are meaning by this. And what would be the boundary condition on the right side? So the right side, let us say there are different possibilities. If we assume that this end is insulated, so then there is no heat transfer across this cross section, then dt by dx would be 0. But let us assume now know that there is a convection from this side also. So because of the convection, there is a heat transfer on the right hand side. So then the heat flow from the body is going to be minus ka into dt by dx. So minus k into dt by dx is the heat flow per unit area, into area would be the total heat flow, and this must be equal to the heat lost due to convection. So heat loss due to convection would be h into area is now cross sectional area, because the heat flow is over this convection is over this area. So that would be h into a, and then t minus t infinity, at x is equal to L. So see, you will notice that dt by dx is going to be evaluated at x is equal to L, and this t is also going to be evaluated at x is equal to L. So this is the second boundary condition. So these are the boundary condition. Again, this equation together with these two boundary condition gives the mathematical model of basically this problem.
Sir,
Yeah.
so can we take temperature as T infinity at x equals to L? That is a boundary condition.
Actually, in general, when you are using a fin, so you would be interested in transferring heat from the some basically the basic system. So that would be at a higher temperature compared to T infinity, because T infinity is the environment temperature. So if that surface has got the temperature as T infinity, so then there is no basically heat transfer. So you could take, but no, that could be one possibility. But in general, we are interested in transferring heat from a body which is at a higher temperature. So that is why I am saying that this is connected to some body which is at a higher temperature T naught, and then the surrounding is at a temperature T infinity. So this is the surrounding temperature, environment temperature. So that is why I
Okay.
am not saying T equal to T infinity at x equal to 0.
Okay, sir. Not x equals 0, sir. X equal
Similarly,
to
when
L.
yeah, if you're
Like
talking
a,
about this T, so that will not be T infinity again. No, there is a some heat flow. If no the temperature at the right in this T infinity, so then there would be no heat transfer from the that section, that from the right end. So BR that is this T is no different from T infinity. So that's actually an unknown, and maybe when we solve the problem, if it comes out as T equal to T infinity, so then there would be no heat transfer through convection at that cross section at the right end. So we are not taking
Okay,
this
sir.
T as T infinity, but different from T infinity. As
Okay, sir.
given that the fin itself is at a higher temperature compared to the environment, and therefore there's some convective heat transfer happening at the right end of the fin also.
Okay.
Yeah. Yeah, so like this, no, for different so problems, you can develop the element level governing equations. Maybe for some problems, we will, when we develop different types of elements, I will be talking about these. Sometimes I would be making use of the energy functionals and so on. So I think now I have given you an idea that how the mathematical model is derived from the physical laws governing a given problem. So in this case, now earlier we have used the equilibrium. Here we have used energy balance. So that's a physical principle. Conservation of energy, that is what we are using over here. And conservation of energy is a physical principle. Using that, we are deriving the element level governing equation. Of course, in the process, we are also using this Fourier law of heat conduction. That is kind of constitutive relation. Like we have in case of solid mechanics problem, we have stress-strain relation, and here in case of heat transfer problem, conduction problem, we have relationship between heat flux and temperature gradient. So that is also kind of a constitutive relation and the boundary conditions. So now coming to, so no, you would have done, so suppose no, you wanted to solve these problems using exact approaches. So you know the how to integrate these differential equations, and then how to find out the constants in the integration process, use satisfying the boundary condition, and therefore you can get the analytical solution. And in some problems, no, for example, this problem you will have complementary function, and you will also have particular integral, and then you will be solving the problem and finding out the constants using boundary conditions. So that is the exact solution. I'm not going to discuss that. I will start now next with the approximate analytical solution. Why I am discussing this approximate analytical solutions is because that is the basis for the development of finite element method. So that is why I know I discussed this approximate analytical solutions. So now I will so approximate analytical no in the exact solution approaches, usually what you do is you try to find a solution which exactly satisfies the differential equations and boundary conditions. But in the approximate analytical solution, you are trying to find out the solution which is approximately satisfying the, at least the differential equations. Boundary condition may be satisfied exactly. Sometimes even both may be satisfied approximately. But most of the time we work with the solutions which exactly satisfy the boundary conditions but approximately satisfy the differential equation. And in the process, if we are able to get a solution which exactly satisfies the differential equation, then it becomes the exact solution of that problem. So usually, no, in this approximate analytical solution, one of the fundamental step is to assume an approximate solution. So we assume some form of a solution, either a polynomial of independent variable, or trigonometric functions or Bessel functions. So those are the various kinds of approximate solution in different forms can be assumed. So let me write what are the steps involved. So the very important step is the basically assumption of an approximate solution. So the first step in the approximate analytical solution is that you assume an approximate solution, and it can be no, generally it is a polynomial, but it can be trigonometric functions, it can be Bessel functions and so on. So but generally, of course, in finite element, the most of the finite elements is a polynomial. So generally a polynomial. So I think polynomial. Anyway, we will be taking examples, so it would be clear what it means. And when we are doing so, that when we are assuming an approximate solution, so we have to, because this approximate solution is going to be substituted in the differential equation. So whatever we assume, it should be differentiable at least up to the highest order derivative present in the governing differential equation. So whatever we assume here must be differentiable up to the highest order. That's at least no, it can be high, no, differentiable higher than what is present in the differential equation, but here what I'm saying is differentiable at least. So let me put differentiable at least up to the highest order derivative present in the governing differential equation. So that means, let us say we are talking about the first problem, that is the that rod problem where load is there. So basic unknown is your u, which is a function of x. So you may assume this u equal to some polynomial a0 plus a1x plus say a2x square, where a0, a1, a2 are unknown constants. This a0, a1, a2 are unknown constant, and this x is the x coordinate. And why up to x square? Because highest order derivative of u is second. So if we take the terms up to x square, we will have non-zero d2u by dx square, and therefore the minimum polynomial we can assume is this a0 plus a1x plus a2x square. Of course, we can add more terms. We can have a3x cube, a power 4x, x power 4, and so on. So this is how the first step we do is, that is, assume an approximate solution which is generally a polynomial. Of course, it can be trigonometric function, Bessel function, and any other mathematical function. And but one important thing is that it should be differentiable at least up to the highest order derivative present in the governing differential equation. So that is one. Then the second step in the approximate analytical solution is that eliminate some of the unknown constants by satisfying the boundary conditions. So usually we try to satisfy the boundary conditions exactly. So therefore, out of some of these constants a0, a1, a2, a0, a1, a2, eliminate some of the unknown constants by satisfying the boundary conditions. And then we will I will take an example, and that time I will demonstrate all these steps. And the third step is substitute the so after eliminating some of the constants by satisfying the boundary condition, then whatever approximate solution we get in terms of the remaining unknown constants, we substitute the resulting approximate solution in the governing differential equation. So substitute the resulting approximate solution in the governing differential equation and after you substitute, so what you can do is, in this process, if you transfer all the terms of the differential equation to the, let's say, left hand side, and in that you put this approximate solution, so you will find that it will not be zero. So whatever we get, a non-zero quantity, we call that as a domain residual. So substitute the resulting approximate solution in the governing differential equation and obtain domain residual. Why we are calling domain? Because that is the domain over which the governing differential equation is valid, and since the solution is approximate, it will not satisfy the differential equation. So some balance, you can say a force or a heat flux energy is going to be there. So we call that as a domain residual. And then once we have got this domain residual, and of course when you assume an approximate solution, you'll have to make sure also that the number of unknown constants are no more than the number of boundary conditions, so that some of the constants are actually left to determine by minimizing the domain residual. That is essentially saying that in some approximate sense we want to satisfy the differential equation. So obtain the last step in the approximate analytical solution is that obtain the remaining constants because after satisfying the boundary condition there still be some unknown constants in the approximate solution. Let us say from the boundary condition you would have got values of a0 and a1, maybe in terms of a2, but a2 is still left as an unknown constant. So we find out this remaining unknown constants, in this case a2, by minimizing the domain residual, appropriately minimizing the domain residual. So obtain the remaining constants of the approximate solution by minimizing. Now this minimize, no, we will discuss what we mean by this. By minimizing the domain residual. So yeah, these are the basic steps involved in the solution, approximate analytical solution of governing differential equations. So I think uh, now the time is almost going to get over, so I will stop here, and I'll take some examples on approximate analytical solutions in the next class, and discuss the associated methods involved in particularly minimizing the residual. So what are the different methods to minimize the domain residual? So we will be discussing that. So I think I want to stop here, and know if you have any doubts and questions, you can ask. So are there any doubts, questions, anybody? Hello, are there any doubts, questions, anybody?
No, sir.
Okay, then thank you all for your attention. I'm stopping the class. Thank you all for your attention. We'll continue on Thursday.
Good day, sir.
Thank you, sir.
Okay. Okay, bye.
Thank you, sir.